discuss the general solution of one-dimensional wave equation. Okay, we know that one-dimensional wave equation are of three types. The first type is this equation for infinite string, and in the second type the string is semi-infinite, and the last type the string is finite. Okay, and we consider here the problem of finite string. Okay, and we use the method of separation of variable, and we consider first the one-dimensional wave equation by the method of separation of variable, and the wave equation is of finite string, and which is given by del 2u by del t2. This is equal to c square into del 2u by del h2, and the length of the string x is given by 0 less x less l, where time t is greater than 0. And this equation can also be written as u tt. This is equal to c square into u xx. We name this equation as the equation number 1. And subject to the initial condition is u x comma 0. This is given by f of x, and ut x comma 0. This is equal to g of x. For 0 less equal to x less equal to l. This is known as the initial condition. This is 2, and the boundary condition is given by u x comma t. This is equal to u l comma t. This is equal to 0 for t greater equal to 0, and this is 3. Okay, and this is very important topic of partial differential equation. Now to use the method of separation of variable, we first let u x t, this is x of x and t of t. Okay, this is the first step of separation of variable. Now we differentiate it. We name this is relation number 4. Now it differentiate with respect to t 2 times and with respect to x 2 times. Then we get u t t x t. This is equal to x of x into this is d to t by dt, because t is a function of t only. Okay, so this is the plain ordinary differentiation. And similarly u x x x comma t, this is equal to d2x by dx2 into t of t. Correct? Now we put the value of utt and uxx in 1. We get the relation as, we get here, this is x of x into, we write this is t double dash t. This is d2t by dt2, and the right side is c square into this is capital X double dash x into t of t. Clear? And we arrange this equation as t double dash t by c square into t. This t we write here, and this is x double dash x by x. Let it be is equal to mu. We let an arbitrary constant, this is mu. And from this relation we get 2 ordinary differential equations. The first one is t double dash, this is equal to mu c square into t, and we name this relation as relation number 5. second one is h double dot, this is equal to mu into x, and we name this relation as relation number 6. Now using the boundary condition 3 in 4, we get this is u 0 comma t, this is equal to x of 0 comma t of t, this is equal to 0. It is given in the boundary condition. Also u l comma t, this is x of l into t of t, this is equal to 0. Now if we take t of t, this is equal to 0, then this is not possible, because at any time we cannot take the function of t, this is equal to 0. Okay, because time is always positive. And so we must have to say that x of 0, this is equal to 0, and x of l, this is also equal to 0. Sorry, this is l. Okay, so our boundary condition 3 becomes another two boundary condition, and we name this boundary condition as relation number 7. Okay, we take here the boundary condition, these are 7, and we get it from relation 3. Okay, now here the value of mu, we say an arbitrary constant mu, it may be of 3 types. First of all, it may be 0, and in the second case it may be greater than 0, and in the last case it may be less than 0. Now we discuss in 3 cases one by one. Okay, case 1, if we take mu, this is equal to 0, then from 5 and 6 we get t double dash, this is equal to 0, and x double dash, this is equal to 0. And clearly h double dash, that is d2x by dx2, this is equal to 0, imply x, this is equal to ax plus b. Integrating we get. Now using the boundary condition and by putting the value of 0 and l, we get x of 0, this is equal to b, this is equal to 0, and x of l, this is equal to al plus b, this is equal to 0, imply we put here b equal to 0, so al equal to 0, imply a equal to 0, and get b equal to 0 from here and a equal to 0 from here, so we get x from this relation, x equal to 0. So this is a trivial solution. Okay, so we reject the case if mu, this is equal to 0. Clear? We reject the case if mu equal to 0. Now in case 2, we take here mu greater than 0, and if mu greater than 0, then we take mu, this is equal to lambda square, this is positive, always positive, whatever may be the value of lambda, where lambda is real. Then the solution of this differential equation and this differential equation becomes, we first solve this equation, we get d2x by dx2 minus lambda square into x, this is equal to 0, and we know that the complete solution of this is x of x, this is equal to c1 e to the power lambda, this is e to the power lambda x plus c2 e to the power minus lambda x. Now we put the value of x is 0 here, so x of 0, this is c1 plus c2, so this is 0, and we put x of l, this is c1 e to the power lambda l plus c2 e to the power minus lambda l, this is equal to 0. And from this relation we get c1, this is equal to minus c2, and getting the relation c1 into e to the power lambda L minus e to the power minus lambda L, this is equal to 0. So this relation gives C1 into sine hyperbolic lambda L, this is equal to 0, and so we must take C1, this is equal to 0, because for all value of lambda, sine hyperbolic lambda L is not always equal to 0. Okay, so from this relation we get C2 also equal to 0, and by putting the value of C1 and C2 equal to 0, from here we get this is x of x, this is also equal to 0. Okay, so from this case we also arrived a trivial solution. Since x is 0, so the solution of u is must be 0, because 0 into something is 0 also. Okay, now we reject the case 1 and case 2, both the cases are rejected. Okay, so here case 2 if mu greater than 0, and case 1 mu equal to 0 and case 2 mu greater than 0 are rejected. When mu less than 0, then we take mu, this is equal to minus lambda square, where lambda is belongs to capital R, that is in real number. And in this case, the solution of this equation, we solve this equation first, we get x double dot minus lambda square into x, this is equal to 0. And clearly, this is plus lambda square x, this is equal to 0. And clearly the solution of this differential equation is x of x, this is equal to a into cos lambda x plus b into sin lambda x, this is the solution. Okay, now put the boundary condition we get already in 7. We put first x of 0, and this gives a into cos 0 plus b into sin 0, so a, this is equal to 0. Now putting the value of a equal to 0 here, and we get x of x, this is equal to b sin lambda x. Now put x equal to L here, because x equal to L, we put that x of L is also be 0, that is x of L, this is equal to b sin lambda L, this is equal to 0. And from this condition, if we take b, this is equal to 0, then we also arrive at the trivial solution. Okay, to get the trivial solution only, we get here sin lambda L, this is equal to 0. And sin lambda L, this is equal to 0, the general solution of sin lambda L equal to 0 given by lambda L, this is equal to n pi, where n belongs to capital N. This is the set of natural number. Okay, so lambda, this is equal to n pi by L here. Now we get the value of lambda, and putting the value of lambda in equation number 5 and solve equation 5. Okay, as t double dash minus, this is plus, because mu equal to minus lambda square, so we get lambda square c square t, this is equal to 0, and we get from here t double dash plus lambda square means n square pi square c square by L square into t, this is equal to 0. And the general solution of this differential equation is t of t, this is equal to c into cos n pi c by L t plus d into sin n pi c by L into t. Okay, this is the general solution of this relation. Now from here we get the solution as x of x, this is given by b into sin lambda x. We put the value of lambda here and get n pi x by L. Okay, and from this relation we get also the value of t. And since we get this value of x for n belongs to capital N, so it looks like this is a sequential solution. Okay, because if we put n equal to 1 here, then we get one value of x. N equal to 2 here, we get another value of x, and so on. So we write this solution as xnx. This is equal to bn into sin n pi x by L for n belongs to capital N. And similarly, from this value we write tnt. This is equal to cn into cos n pi ct by L plus bn into sin n pi ct by L. Okay, and we get the value of this from 4. We write it as unxt. This is equal to xnx and tnt. Okay, and this is given by, we multiply xnx and tnt and get bn into cn cos n pi ct by L plus bn into sin n pi ct by L into sin n pi L by n pi x by L, and this is for all n belongs to capital N. We get the value as this. Okay, and if we take these two arbitrary constant as one arbitrary constant and dn into dn and another arbitrary constant, then we can write this equation as en cos n pi ct by L plus fn into sin n pi ct by L into, this is same, sin n pi x by L, right, where en we let, this is bn into cn, and fn, this is we let bn into dn. Okay, we get two arbitrary constant or two sequence of arbitrary constant. This is en and this is fn. Now we use the initial condition given by 2. This is u of x comma 0, this is equal to f of x, and ut of x comma 0, this is equal to g of x. We use the first relation u of x comma 0, this is equal to f of x. To use this, we put t, this is equal to 0 here. So we get u of x comma 0, and the right side is n, this is equal to 1 to infinity. We put t, this is equal to 0. So we get, this is e n into cos 0, this is 1. And this term is 0 because sin 0, this is equal to 0 into sin n pi x by L. Okay, that is we get fx, this is equal to summation en into sin n pi x by L, n equal to 1 to infinity. Okay, we get one relation. This is very important relation of the solution. And now differentiate with respect to t. We get ut, then we put t equal to 0 here. We get the derivative of this term is ut x comma t. This is equal to, differentiating with respect to t, we get, this is summation n, this is equal to 1 to infinity, and this is n pi c by L into en sin n pi ct by L, this is minus, and this is plus. We take common n pi c by L also from here and get Fn into cos n pi ct by L into sin n pi x by L. This is constant with respect to t. Now we put at t equal to 0, we get ut x comma 0. This is summation n equal to 1 to infinity. This is n pi c by L into minus en into 0, because sin 0 is 0 and this term is Fn. Here we get Fn into 1 and this is sin n pi x by L. Correct? And putting the value of ut x comma 0, this is g of x. G of x, this is equal to summation n equal to 1 to infinity n pi c by L into Fn. We here give a bracket with two constant into sin n pi x by L. Okay, this is also another important relation related to the solution. Now from these two relations, this and this, it is clear that we write the general solution of the equation. What is the general solution? The general solution of the equation, that is u x comma t, this is equal to summation n equal to 1 to infinity. We use here the superposition or principle of superposition. Okay, and this is summation u n x t, right? And the solution be written as summation n equal to 1 to infinity e n into cos n pi ct by L plus f n sin n pi ct by L into sin n pi x by L. And this is the general solution of one-dimensional wave equation by separation of variable. Okay. Now we have to find the arbitrary constant En and Fn. This is the Fourier series of fx. Okay, and we also say that in detail this is the Fourier sine series of fx. And clearly this is also the Fourier sine series of g of x. So to find the Fourier coefficient, here the Fourier coefficient is En and here the Fourier coefficient is this term. We give the bracket here. Okay. Now to find the Fourier coefficient, we use the formula of Fourier coefficient of half range series or Fourier sine series. And from Fourier sine series, we can write this relation or En as this is 2 by L, because this is half range series and the range is 0 to L. So this is 2 by L into integration 0 to L, okay, 0 to L into fx into sin n pi x by L dx. Okay, and similarly from this series we get here the Fourier coefficient is the total term n pi c by L into Fn. This is equal to 2 by L into integration 0 to L. This is g of x into sin n pi x by L into dx. And from the second relation, Fn, this is equal to L cancel out, 2 by n pi c into integration 0 to L g of x into sin n pi x by L dx. Hence we say that this relation is the general solution. This relation is the general solution of the one-dimensional wave equation by the method of separation of variable together with the given initial and boundary condition is given by u x comma t. This is equal to this side, where the arbitrary constant en and fn are given by this and this relation. Okay, this is the complete solution of the wave equation. Thank you for watching.